In this section, we're going to look at the relationship between free energy, G, and the equilibrium constant K, which makes sense if you think about it. The more spontaneous a reaction is, it's because it creates more products than reactants. Of course, if we have a G value that is deemed non-spontaneous, that means it has an equilibrium which stops before we make more of the products than reactants. So we can look at those relationships directly. Just as we can look at how the concentrations affect spontaneity, we can also say, oh, okay, well, if the delta G real is at equilibrium, then we can now solve for the equilibrium constant itself. So we've got delta G real becomes 0. Now that means Q must be at K. So then we could just rewrite this equation to find the equilibrium constant itself. Delta G standard equals negative RT ln of K. It also means that it can go the other way around. If we know the value of K, we can now find the delta G. So we can really go back and forth in both directions here. And, these equations are the same. I would just pick the one that's easiest. This top one is good if you're trying to find delta G. The bottom one is good if you're trying to find K. So let's start with a reaction we're familiar with. If you put NaCl in water, it dissolves. It turns out this reaction has a K of approximately 37. So if we plug that K value into our ln of K times the temperature in Kelvin at room temperature, which is 298, times our R value in kilojoules, we get a value of about 9 kilojoules per mole negative, right? So a negative value clearly implies this is spontaneous. We have a K value which creates more products than reactants. All of this makes sense. Okay, so try this one for lead chloride. It has a KSV of 1.6 times 10 to the negative fifth. Find the delta G standard based on that KSV. So if you remember back to 151, we said that lead chloride was an insoluble salt. And that isn't quite right. Lead chloride dissolves, it just creates very, very few products. So in this case, we're going to get a K value of 1.6 times 10 to the negative fifth. Now, right off the bat, because we have a K value smaller than 1, we are going to end at equilibrium with fewer products than reactants. And so when we solve for delta G standard, we are going to assume delta G standard says non-spontaneous. Why? Because again, delta G standard only says spontaneous if we are creating more products than reactants. So if we plug in this K value times the temperature in Kelvin times the R value in kilojoules, we get a positive value of 27.3 kilojoules per mole. Again, positive value means this reaction is non-spontaneous under standard conditions, which just means we have fewer products than reactants. All right, so we've got another reaction. We've got a delta G standard value at negative 32.8 kilojoules. What is the equilibrium constant K for this reaction at 23 degrees Celsius? In this case, we're using the equation E to the power of the negative delta G standard divided by RT, where R is 8.31 joules per mole K, and T is the temperature in Kelvin. So I usually break this up into parts. So we're going to look at the to the power of section. Since it's negative delta G, and we've got a negative delta G value, those two negatives will make a positive. Since our R is in joules, we're changing it to kilojoules. And since our temperature is at 23 degrees Celsius, I went ahead and moved it to 296 Kelvin. So if we multiply all that out, that gives us e to the power of 13.33, which gives us a K value of 6.15 times 10 to the sixth. This is the same reaction. Delta G standard is negative 32.8 kilojoules, but go ahead and try it at 400 degrees Celsius. So this problem is almost exactly the same as the last one. We have a delta G standard of negative 32.8 kilojoules, The temperature is now at 400 degrees Celsius. So before we go any further, we're going to add 273 to get a Kelvin temperature of 673 Kelvin. Our equation is e to the power of negative delta G over RT. Since it's the negative of a negative delta G, that becomes positive 32.8 kilojoules over our R value of 0.00831 kilojoules per mole K times 673 Kelvin. So all of that is to the power of, so now we have e to the power of positive 5.86, which gives us a K value of 350. So this problem is a little bit more complicated than something we will typically do, but it does demonstrate how we can use a delta G standard value to get a real chemical concentration. So in this case, we have N2 gas reacting with O2 gas to create 2NO as a product. The above reaction is at equilibrium at 353 Kelvin. If N2 and O2 are both measured at 0.45 atmospheres, what is the pressure of NO? So what we have to do is use the e to the power of negative delta G over RT equation equals K to find the equilibrium constant K. Once we know the equilibrium constant K, we can use that with the reactant concentrations to find our unknown concentration of NO. So we are going to set up this equation e to the negative delta G over RT. Our delta G is negative 14, so negative delta G gives us negative 14 kilojoules, which works out to a positive with the double negative. That is over 0.0083 kilojoules per mole Kelvin times our temperature of 353 Kelvin. That gives us e to the positive 4.77, or an equilibrium constant of 118. Now, when we set up our equation, K equals NO squared over N2 times O2, we know our reactant concentrations are both 0.45, so we can cross-multiply those to get 118 times 0.45 times 0.45 gives us NO squared. If we take the square root of both sides, we get a concentration for NO of 4.89 atmospheres. Again, we're unlikely to have anything like this in the homework or on the exam, but it is just a good way to see how all these things can become connected together.